Welcome to this lecture on recursive algorithms. We're going to study two examples of recursive algorithms, starting in this segment with a very simple one. So consider the following problem. You are given one non-negative integer k and you are asked to compute the value 2 to the power k. Now before you start designing the algorithm, you should always analyze the problem. Here the analysis is simple based on the definition of the exponential function to the power 2. So 2 power k is equal to 2 times 2 times ... times 2, where 2 appears k times. So how many multiplications are there in this product? Well, there are only k minus 1 of them, one less than the number of 2's, because each multiplication appears between two consecutive 2's in this product. Now let's look at some special values for k. When k is equal to 1, 2 power 1 is 2. Notice there are no multiplications in this expression, just one occurrence of 2. And when k is equal to 0, 2 power 0 by definition of the exponential function is 1. So according to this analysis, we must design an algorithm that computes this product. So the obvious way to start thinking about it is to design an iterative algorithm, that is, an algorithm with a loop. Now let's go ahead and write down this algorithm in pseudocode. We start with a keyword function because this algorithm is going to return a value. Let's give it a name. We'll call it power of 2. This algorithm takes a single argument, a non-negative integer k, using the same name for the variable as the one we used in the problem statement, and we're going to return an integer. Now we're going to use a variable to store this product, and we're going to obtain this value by executing a loop that repeatedly multiplies that product by 2. Now what should be the initial value of the product? Well, it should be the smallest value that we can return, which is 1. So let's call this variable p for product or power, and let's initialize it to 1. Then we're going to have a for loop for I equals 1 to k, and all we need to do in the for loop is to multiply p by 2. Now at the end of the for loop, the final value of this product, that is 2 to the power k, will be stored in p, so we can just return it. Now one question we should answer right away is, why do we have k iterations of that loop, even though we said we would only have k minus 1 multiplications? Well, the answer is because we're starting at 1. So even to get the first 2 here, we need to multiply p by 2. To get the second 2 into the product, we need to multiply it again by 2. So to get 2 to the power k, we need to multiply p by 2 k times. So you have one extra multiplication compared to here, because in essence, this product really starts with an extra multiplication here, namely 1 times all of this. So we always have to check the correctness of our algorithm. So if k is equal to 1, for example, then p is going to be initialized to 1. There's only going to be one iteration of this loop. P is going to be multiplied by 2, and the value 2 is going to be returned, which is correct. Now what if k is equal to 0? Well, it's going to work as well because of this initialization here. So p gets 1. For I equals 1 to 0 means the loop doesn't get executed at all, and the value of 1 is returned, which is correct for 2 power 0. Now let's go back to the topic of this lecture, which is recursive algorithms. What is a recursive algorithm? Well, by definition, it's an algorithm which refers to itself or calls itself inside of its own body. Notice this algorithm is not recursive because it does not call power of 2. This is just an iterative algorithm. It's based around a loop. So let's try to design a recursive algorithm for this same problem. Remember that a recursive algorithm to compute this function of k, say f of k, would be an algorithm that calls f on a smaller value for k, for example, k minus 1. So one way to analyze this problem to exhibit a recursive formulation is to rewrite this product, which we can call f of k, to exhibit the term f of k minus 1 inside of it. Now what is f of k minus 1 in this case? Well, it's 2 power k minus 1. And in particular, notice 2 power k minus 1 is right here. It's this product of all the 2's except the first one. In other words, one way to rewrite this 2 power k is 2 power k equals 2 times 2 power k minus 1. And here is the recursive call, if you wish, appearing. Now, of course, this expression only works for k greater than 0. Because if k is 0, 0 minus 1 is a negative power, which we don't want. So, since this is the recursive case, we need to have a base case. The base case will be when k is equal to 0, and we already know the answer. F of 0, or 2 power 0 in this case, is 1. So, let's write a recursive algorithm. We're just going to change the name in the header line to power of 2 rec for recursive. And now all we have to do is to check which case we're in. If k is equal to 0, then we are in the base case. We can return 1 directly. Otherwise, we're in the recursive case, and all we have to return is 2 times power of 2 rec with the argument k minus 1. And this is one recursive definition of an algorithm for this problem. So again, we have illustration here of a base case, a recursive case, and notice in a recursive case the function calls itself with a smaller argument than it started out with. That's the guarantee that the recursion is not go on forever and will eventually hit the base case. Let me wrap up this segment by listing a few recursive algorithms that you should be familiar with. So one example of a recursive algorithm is the one to compute a to the power k. It's just a generalization of this problem when 2 is generalized to any real number a. The second recursive algorithm would be one to compute n factorial. That's probably the most famous recursive algorithm. Another example would be a recursive algorithm to compute a to the power k modulo n. Yet another recursive algorithm is very popular to compute the greatest common divisor of two integers, m and n. And we could also write a recursive algorithm for the linear search problem. Remember, linear search or sequential search was discussed earlier as an iterative algorithm when you use a loop. Make sure you know how to write a recursive version of this algorithm to solve the same problem. Similarly, for binary search, we wrote an iterative algorithm to solve this problem. I encourage you to go ahead and write your own recursive version to solve the same problem.